Okie dokie. Welcome back to your favorite class. Not a lot of your favorite class left. Man, we only got like a week left. Dang, not even. Truth hurts. Or the truth sets you free. I'm not sure. Announcements. Number 1. Simulation 3, due today. Hopefully you got it in. If not, get it in. What are you doing? All right. Announcement number 2. That is your homework number 6, which is the last homework for the class. It's on gears. It's going to be due on Hoo-Ha 2 times Tuesday. So a couple days from now, get it done. Get the weekend to do it. Announcement number 3. That is that your exam number 3 for the class, or I've kind of like listed it as the final exam here, is going to be a week from yesterday. So the 21st of May, which is that Thursday. All right, those are your announcements. A couple other things I want to say. We are through the material for the class. I've taught you everything that I think we need to teach you. What we're going to do from here on out is basically prep for final exam or exam number 3 or reinforcement of knowledge. Okay, so we're going to look at kinematic analysis of linkage today. It's an example problem. And on Tuesday and Wednesday, I'm going to be going over practice problems from the exam 3 practice problems that I handed out. That's also on Blackboard, by the way, under the exam prep tab. So there's practice problems there related to impact, momentum, kinematic analysis of linkage, and gears and gearing systems. So look at that. Full solutions also posted for that. Next week, Tuesday and Wednesday, I'll just be going over those practice problems in class. So if you want to come and check those out and go through the review problems, great. Come and do that. If you think your time is better spent doing other things, fine. I'm trying to get you ready for exam number 3. So if you want to come and check it out, great. If not, that's fine too. I'm not going to kind of get in your grill about it. So I'm giving next week. We got through all the material that we needed to get through, so I'm happy as long as you're happy. All right, so I'll chill, like I said, give you guys a little break next week, and if you want to come check out some review problems, come check out some review problems. Got it? Got it. Without then further ado, I'll talk about what we're going to do today, and that is a kinematics analysis on linkages. I purposely waited until the simulation was over to talk about this because I didn't want more confusion about linkages before you submitted your simulation. So if you're still working on your simulation, what are you doing? You should have got it in, but whatever. Hopefully you're not confused by the discussion today. I added to the linkage link on Blackboard, linkage link. Yeah, I added to the linkage link on Blackboard an addendum that has these slides that I'm about to show you guys. All right, so if you're trying to follow stuff along on Blackboard, okay, the notes on your own computer, it's on Blackboard under the linkage tab in the lecture notes. All right, so I'm going to bring those into focus now for all of you guys. And this is an addendum to the linkage analysis that we've done. All right, so 4 slides here. 3 things I just want to voice over for a second, and then an example problem that we're going to do. What we've talked about during weeks 6 and 7 for linkages, which is just a couple of weeks ago, we did the complex vector notation, and we generally went through what I would consider the algebraic solution for this. All right, we took derivatives of these vectors and we equated everything all nicely, and we came up with an expression for theta 3 and theta 4, as well as an expression for omega 3 and omega 4 that was all based on little a, little b, these link lengths and the various angles, and everything was just algebraic, and that's good when you're going to code things up in a MATLAB, which is what you guys did for simulation number 3. However, if you're kind of on the job and on the fly and you want to do some analysis and you don't remember that exact omega 3 equation, which is something like omega 3 is a omega 2 divided by b times sine of stuff, okay? If you don't remember that off the top of your head, I bet that you will remember the kinematics equations that we talked about in week number 2 and number 3, because you've written them on your homeworks 50 million bazillion times. All right, so I want to go through kinematics analysis because it's more useful to go through the analysis of kinematics by hand, and it's easier, in my opinion, to recall kinematics analysis of linkages than it is to recall the algebraic analysis that we did, where we did complex notation and all that sort of stuff. Okay, so I'm going to go through what is the full kinematics analysis, which is akin to things that we did in weeks 2 and 3 on this linkage, just to refresh your memory in your mind on how this kinematics analysis is done. All right, so here's the algebraic solution. I'll talk about it quickly. You've got this 4-bar linkage. It's got an open and a cross configuration. That doesn't change. Obviously, there's no way to get around that. And we looked and we saw that you could have position analysis giving you two possibilities for these angles of theta 3 and theta 4, and that is an open and a cross configuration. If they're not equal to each other, theta 3 and theta 3 prime, they're both real, then you have this dual configuration. If you just have one value, then you have one configuration, and if you get an imaginary solution for theta 3, it can't be constructed. You should have seen all three of these possibilities in simulation number 3. If you didn't, you made a mistake. All right, so you should have seen all three of these conditions in simulation number 3. Now, we looked at the algebraic solution, which we sort of went through and glossed over and said that, all right, in the algebraic solution, you could just come up with these expressions that are general for like omega-3 and omega-4. Sorry, guys, my dog is like, all up in my grill right now. I think he's just like wants to go outside. It's beautiful out there. All right, so omega-3 and omega-4, there are your equations for them, and then you can get the velocities using this kinematic analysis. All right, let's say you don't remember what those equations are. I don't have that memorized. I don't know what that is. Is it sine theta 4 minus theta 2 or theta 2 minus? I don't remember, okay? Alternatively, you can just go back to your kinematics, which we talked about in like weeks 2 and 3, to do an analysis on these linkages. And in my opinion, it's probably easier that way. It's a little easier to understand. It's more XY coordinate system friendly, so on and so forth. So that's what we're going to do today. Remember, we have these general relationships between velocities of these particular pins in the system, angular velocities of the individual pins, and then the position vectors that locate all of those pins. So these 4 equations, 4, are all you really need to do the kinematics analysis of the linkage. That is the velocity kinematics analysis. So VA, velocity of B with respect to A, velocity of B, and this relative velocity relationship, which you should have learned in 2002, and hopefully it's stuck in your brain, is that the velocity of B is A plus velocity of B relative to A. All right, so let's do a practice problem using kinematic analysis of one of the test configurations from simulation number 3 so that we know we have some verifiable numbers. All right, so test configuration number 1 of simulation number 3 had these particular values, and we're going to go through the kinematic solution with these particular values just to hammer home, bam, that kinematics knowledge that should be buried in that brain, buried in there. Brr. All right. So I'm going to copy this information over to the writing pad, and I'm going to bring the model in, and we're going to do it. Here's your information. And let's look at your model, which will be helpful for us in this problem. I've gotten really good at like this touchpad on my laptop. Usually I use a mouse when I'm in the office. I don't get a lot of practice with the touchpad, but I'm getting better with this touchpad. A little bit annoying to like get used to it at first, but I'm kind of getting there, forcing myself to learn. Learn even at the ripe old age of 31 years old. You still learn new things. All right. All right, so away we go. Got a 4-bar linkage with the following variables: A, B, C, D, and our drive angle theta 2. All right, so these are all things that we know. Link length A, link length B, link length C, and the length between the pin positions, the value D. We also know the drive angle theta 2 is 40 degrees. That's here. All right. After position analysis, you have an open and a cross configuration. So we're going to assume that we've calculated theta 3 and theta 4 for both the open and cross configuration. And now we're going to do kinematics analysis to determine the velocities of the various points and the angular velocities of the various links. All right. So using only kinematics. All right. So we're going to use what are the equations that follow. VA is omega 2 cross R2. VB is omega 4 cross R4. These are easy to see because A and B can be found from the pins O2 and O4. So here's O2 and O4. So we know that we can get the velocity of A and the velocity of B by something like R cross omega 2 for this particular link, and R cross omega 4, or omega 4 cross R for that particular link. All right, so those guys, pretty straightforward. We also have the idea here that the velocity of B relative to A is omega 3 cross R3. That comes from this sort of second link in the chain, where we're going to assume that A is like pinned and determine what the relative velocity of B is relative to A. This is like if A was fixed, what is the fixed axis rotation of B about A? And then the last relationship that we have is that the velocity of B is also a combination of the translational velocity of A plus the fixed axis rotation of B about A. All going back to week number 2, all right? Actually, week number 1, we had fixed axis rotation equations. So this class is coming full circle, right? Quite appropriate for fixed axis rotation that it's coming full circle. Yeah, okay. It's circular rotation, get it? Yeah, okay. Oh, man. Quarantine, it's rotted my brain. Let's do it. Here we go with our kinematics analysis. First is regardless of open or crossed, the velocity at A is the same. And that's because this particular link here doesn't have alternate values. Theta 2, the driving angle, is whatever it is. There's no open or crossed theta 2 value. It's all just one thing. All right, so with that statement in mind, we will say then that the velocity of A is omega 2 cross R2. Omega 2 is given up above in the problem statement, 10 radians per second. It is the angular velocity of the driving link. So here's 10 k hat radians per second. And I'm going to cross that with this position vector R2. So for R2, that's this particular link in the chain. So we'll need little a in the drive angle theta 2. So little a, 30 millimeters, drive angle theta 2 is 40 degrees. So this can allow us to define our position vector R2, which is something like 30 millimeters times the unit vector that defines that particular direction, which is cosine 40 I hat plus sine 40 j hat. Capiche? Run this down, you'll find that the velocity of A after doing your cross product, negative 192 I hat plus 230 j hat millimeters per second. So this is the velocity of pin A in your typical XY coordinate system. All right. Moving on. This is like the first of our 4 equations that we're working with. The second of our 4 equations that we're working with, the velocity of B is equal to omega 4 cross position vector for the third link in the chain, which is given by R4. Alrighty. Well, here we're looking at what would be this guy. We're pinned about 0.4. So if I want the velocity of this point here at B, then I can just do omega cross R around that pinned location, which is exactly this arrangement. The problem, I do not know what omega 4 is. It's something that I'm hoping to solve for with this kinematics analysis. So I will leave that as an unknown, and I know that it's rotating in the z direction or about k hat. I'm going to cross that with position vector 4, which will have to make a selection for the open or cross configurations now, because that position vector is different in the open and cross configuration. As you can sort of like obviously see in this image, we have 2 different position vectors that we could use for R4. Let's focus on the open configuration here. first, and know that if you wanted to do analysis of the cross configuration, you could just put in alternate values for, let's say, theta 3 and theta 4. All right. So we're going to focus on the open configuration. That means we're going to pull this number for R4. That is 102.9 degrees. And R4 also uses the variable little c, which means we're going to pull this value of 95 millimeters. So in that particular situation, if we want to define R4, it's going to be something like 95 millimeters times the unit vector upon which lies, which is cosine 102.9 I hat plus sine 102.9 j hat. So finally, my expression for the velocity of B, which will contain the unknown omega 4, after doing my cross product, negative 92.6 omega 4 I hat minus 21.2 omega 4 j hat. Let's call this equation number 1, because we're going to have to come back to that because we've got an unknown omega 4 floating there. All right. So far, we've used 2 of our 4 equations for kinematic analysis. Let's move on. The next equation that we want for our kinematic analysis is something like the velocity of B relative to A, which is kind of like dependent on link number 3. Here's omega 3 cross position vector R3. All right, omega 3 again is unknown known. So we have omega 3 k hat crossed with my position vector R3. Again, I'm going to focus on the open configuration, and we'll come back to the cross configuration later. So for defining R3, I need theta 3, which again is this angle here, and I need the value of little b, which is given in the problem, 75 millimeters. All right, so here this is going to be something like 75 millimeters times. The angle here is, for theta 3, 78.8 degrees, so cosine 78.8 I hat plus sine 78.8 j hat. All right. This will give us the velocity of B relative to A. Again, the omega 3 is floating like a fish. Have your fish oil omega 3s. It's going to be negative 73.3 omega 3 I hat plus 15.8 omega 3 j hat. This here is equation 2. All right, continuing. The last kinematic relationship that we have to solve this problem is the general velocity relationships between A, B, and their relative velocities. So the velocity of B is the velocity of A plus the velocity of B relative to A. All right, this we know, we solved for already. This here comes from equation 2. This guy from equation number 1. So we execute that. You'll get the velocity of B, which is on the left-hand side here, negative 92.6 omega 4 in the I hat, minus 21.2 omega 4 the j hat. Okay, that comes from equation number 1 above here. The velocity of A comes from all the way back up at the beginning when we did this. So velocity of A is negative 192 I hat plus 230 j hat. And adding to this the velocity of B relative to A, which is just right up here, negative 73.3 omega 3 I hat plus 15.8 omega 3 j hat. All right. So here now we have 2 equations, one in I, one in J, and 2 unknowns, omega 3 and omega 4. All right. So 2 equations, 2 unknowns. And so let's get after it. The first would be in the I hat direction. We're going to have on the left-hand side, negative 92.6 omega 4. On the right-hand side, we'll pull negative 192 and negative 73.3 omega 3. This is equal to negative 192 minus 73.3 omega 3. And here we've got two unknowns, so let's just solve for one of them. I think since omega 4 is on the left-hand side, let's just divide everything by negative 92.6, and we'll kind of work itself out. This will be 2.07 plus 0.792 omega 3. All right. Let's call this equation number 3. And lastly, we can look at what's going on in the j-hat direction. And so I'm going to pull information here for j-hat, here for j-hat, and here for j-hat. All right. So in j-hat here, then we have negative 21.2 omega 4 is equal to 230. It's when I go to the dentist, tooth hurty, plus oh man, 15.8 omega 3. God, the jokes, I just ran out of material. I'm out of material, guys. I'm sorry. What do you want me to do? All right. So let's plug in 3. It's the time that I go to the dentist, tooth hurty. Negative 21.2 times omega 4 I'm plugging in here. 2.07 plus 0.792 omega 3 equals 230 plus 15.8 omega 3. All right, only unknown here is omega 3. I'll trust that you guys can do algebra, though, you know, little suspicious. All right, gives us omega 3 negative 8.4 radians per second. All right. Now back into 3 would get us omega 4. So here, remember that omega 4 is 2.07 plus 0.792 omega 3, or 2.07 plus 0.792 times negative 8.4, and you're going to end up with omega 4 here is going to be equal to negative 4.6 radians per second. All right, sweet. This is how you would utilize the kinematics analysis to get you your angular velocities of links number 3 and links number 4. How are we doing? Got any questions? Any angry notes about my terrible jokes? The real Kevin Hart. That ain't it. What ain't it, Caleb? Did I copy something wrong? I hope not. Should have raised your hand. You guys see that there's like this raise your hand option now? They didn't have that before. Like, when did that get there? That's 230. That's my best material. That's all I got. I got nothing left. I'm out of the goods. All right. We got no more goods. Only bads. All right. So we could check this omega 3 and omega 4 using our algebraic solution. All right. So let's check these guys at the algebraic solution. All right. And we have something, remember, like omega 3 is A omega 2 on B times, I got to get this fraction right here, sine of theta 4 minus theta 2 divided by sine of theta 3 minus theta 4. It's hard to remember. Like, it's hard to just memorize this because it's so similar to the equation for omega 4. So I have problems memorizing it, which, you know, translates to, I think, you guys having difficulty memorizing it. But maybe you guys memorize stuff better than me. I would be the worst actor in the history of Hollywood if I tried to be an actor, because my memorization skills for like learning lines and learning lyrics of songs is horrible. Okay, I can listen to a song 100 times on repeat and not know the lyrics. Some people hear it 3 times and they're like, I know every word. I'm like, how the hell do you do that? That's equations I'm better with, but goddamn, like memorizing stuff, terrible. All right. So anyway, let's get back to it. A, given in the problem, was 30 millimeters, to remind you, times omega 2, 10 radians per second, divided by little b, given in the problem, is 75 millimeters. This is going to be multiplied by the fraction that is sine of theta 4. We're looking at the open configuration still, so 103, 102.9, but I rounded here. 103 minus 40. 3 significant figures, that's enough. That's all you get as an engineer. 3.14, that's all you need, right? That's all pi is, 3.14. Slop off the rest, who cares? Theta 3, again, we're taking the open configuration, 78 minus 103. Punch these into your handy-dandy calculators, beep boop, beep boop, beep boop, and you'll get omega 3, negative 8.4 radians per second. Hey, it matches. Good things. You could do the same thing for omega 4, slightly different equation. Here, it's really the thetas that like throw me off, because the thetas for omega 3 and the thetas for omega 4 in the sine argument are not the same. So it's annoying. All right, so there you go. There's your expression for omega 4. Plug all this in. A is 30 millimeters, 10 radians per second for omega 2. Little c, 95 millimeters. Here we have sine theta 2 minus 3. This is 40 minus 78. And in the denominator here, we have theta 4 minus theta 3. That's 103 minus 78. Plug this in. Beep boop, beep boop, beep boop. Negative 4.6. Rads per second. Isn't that rad? All right, so our algebraic solution matches our kinematic solution. And that's good, because the algebraic solution is basically derived from the kinematic solution. So it better match, or else we messed up. All right. I really want to go through this exercise because I don't want you guys to lose the kinematics. Don't lose that power. It's like when Superman's right by the kryptonite, all right? I don't want you to lose your kinematic superpower because you're near the kryptonite, which is the algebraic solution, all right? Don't let that algebraic solution be your kryptonite. Or don't let the MATLAB run button be your kryptonite. All right, we already solved for the velocity of A. All that we really need to complete the problem is the velocity of B. And all the way back up here, way back here, we had this general expression. Remember when I wrote that number 1? You're like, what a silly goose. He's never going to use that number 1. Ha-ha! I'll have to use that number 1 right now. It's like I planned that. Go back into... Ha-ha! Silly goose. Back into number 1. You're going to end up with negative 92.6 times omega 4 I hat minus 21.2 omega 4 in j hat. So we plug in. Omega 4 we found, negative 4.6 radians per second minus 21.2 times omega 4, which is negative 4.6 radians per second. Finally, velocity, pin B here is going to be 426 I hat plus 98 j hat millimeters per second. Sweet. There you go. Full kinematic solution for the open configuration. You would have to go through a similar analysis for crossed configuration if you wanted, just use the values of like theta 3 prime and theta 4 prime to get you there, right? You'd have a different velocity at B. It'd be something like VB prime, which would be for the crossed configuration. Cool? Understand? Rubber band? There are some problems that are similar to this on the exam review. and I'd like you to give a stab at them using this kinematic solution. All right, I think it's good for you. Kind of bring the class full circle. All right, that's going to be it for today. Get you out of here in about 30 minutes instead of the full lecture. So go enjoy that weather outside, but stay away from other people. All right, thanks for coming. Come on Tuesday if you want to see some review problems. Otherwise, see you for the exam, I guess.